Good day and welcome back for the fourth part of our discussion on differentiation formulas. In the previous videos, we've introduced all of the relevant formulas, so now is the time for a few quick reminders and then some additional practice problems. So in terms of our differentiation formulas, I would say that we have 6 key formulas. We saw that the derivative of a constant is always going to be 0, regardless of what that constant is. We also saw that if we had the derivative of a constant times a function, you can simply pull that constant outside of the derivative. We have the power rule that tells us the derivative of x to the n is nx to the n minus 1. If we differentiate a sum, it becomes a sum of the derivatives, and the same thing if it's a difference. And lastly, we have the differentiation rules for a product and a quotient. The product rule tells us that the derivative of f times g is the derivative of the first times the second plus the first times the derivative of the second. And for a quotient, we get low d high minus high d low all over the bottom squared. And I assure you, as you go through and practice more and more of these examples, these formulas will become second nature. In fact, many of these are formulas you will use hundreds of times throughout your calculus experience. Let me just note that one particular example of the power rule that we encounter frequently would be the derivative of a constant times x. And applying the power rule using n equals 1, the derivative of this is simply going to be c times 1x to the 0, and x to the 0 is 1. So this is a frequently encountered formula which comes from the power rule. With this in mind, let's go ahead and move on to a few more examples. The first of which is, let's find the points on the curve xy equals 12, at which the tangent line is parallel to the line 3x plus y equals 0. So at first glance, this seems like a rather tough problem, maybe even tough to understand exactly what they're asking us to do. So let's begin by simply just illustrating this with a picture. So if we think about the curve xy equals 12, note that's y equals 12 over x. So what that should look like is the graph of the reciprocal function 1 over x. So roughly speaking, it's going to look something like this. So this is y equals 12 over x in blue. Now, what we are asked is to find the points on this curve where the tangent line is parallel to the line 3x plus y equals 0. So that line could equivalently be written as y equals minus 3x. So a line going through the origin with slope minus 3. So roughly speaking, and without scale, it's hard to tell exactly what it is, so we'll just have to go with this, y equals minus 3x. And the question is, at what points on the curve will the tangent line be parallel to this red line? And it looks like there's maybe 2 spots. So a point in the third quadrant and then some corresponding point in the first quadrant. So roughly speaking, if we throw those lines in, it looks like maybe right about here, and then this corresponding line corresponding to that should be a single point of tangency in the third quadrant. So it looks as though there should be 2 tangent lines that have a slope of minus 3. Now, note we've sufficiently kind of restated this question just by going through the process of drawing the picture. So stated differently, what we are trying to determine is what are the points, on the graph of the curve given by f of x equals 12 over x, where f prime of x is equal to minus 3. That is, when will the slope of the tangent line be minus 3? So note f of x equals minus 3, i.e. the slope of the tangent line is minus 3. So let's go ahead and do some calculus. The function we are dealing with, 12 over x, if we want to differentiate this, take a moment and think about what rule would be the easiest for you to apply. And note, in its current form, you certainly could apply the quotient rule, but a small algebraic rewrite, 12x to the minus 1, allows us to hopefully very efficiently apply the power rule. So we can use the power rule with n equals minus 1. So we would have that minus 1 comes down front, and the new power is 1 less. That is, f prime of x is equal to minus 12 x to the minus 2. And if we rewrite that again, we would have minus 12 over x squared. And what we would like to know is, when is f prime of x equal to minus 3? So we have a formula for f prime of x, and we want to know what are the values of x that will make that equal to minus 3. And I have placed the question mark over the equal sign just to indicate that we are trying to solve for the quantity of x that would make this equation true. So now if we want to isolate and solve for x, we would multiply both sides by x squared and divide both sides by minus 3. So the values of x that would satisfy this would be plus or minus 2. But we do have to be very careful to make sure that we're answering the desired question. We want to find the points on the graph of this function that satisfy this. So we have to think about what are the points that correspond to x being positive 2 and x being negative 2. And if we look back at our function, when x is equal to 2, f of x is going to be equal to 6. And when x is equal to minus 2, f of x is going to be equal to minus 6. So note, the first 6 is f of 2. The minus 6 in the second point is coming from f of minus 2. And these 2 points correspond to the solution that we are looking for. In our picture that we started with, note the 2 points that we have, 2 comma 6, minus 2 comma minus 6. So the picture is not perfect, which is okay, but it does give us the relevant information that we need and the intuition that allows us to get started on the problem. Let's look at maybe a bit clearer of a picture. If you were to use a computer program like GeoGebra to sketch the graphs, we would have those points 2 comma 6 and minus 2 comma minus 6, where the slope of the tangent line would be minus 3. So let's move on to one additional common example that we will encounter. Find the equation of the tangent line to some given function at a value of x. Now, what I want to note is, before we do any work whatsoever, we know exactly what the form is going to be for this tangent line. So note, the form of the tangent line is going to be y equals f prime of 1, the slope, times x minus 1 plus f of 1. That is the line with slope f prime 1 through the point 1 comma f of 1 in the xy plane. And this very nicely illustrates to us that we need to find two quantities. What is the function value f of 1? What is the derivative value f prime of 1? The first of which we can find almost immediately. So f of x is equal to 1 plus the square root of x over x squared. And if we substitute in 1, we'll get 1 plus the square root 1 over 1 squared, which is 2 over 1, or 2. So we've determined our first of the two values. We now just need the derivative. And this is where I'd like to ask you to maybe do a bit of work. We have the function f. I would like you to spend, I don't know, maybe say 2 or so minutes and see if you can find the derivative f prime of x. And I will note, as usual, you have several different approaches, but some algebraic simplification may lead to an easier differentiation process. So find that derivative. So assuming you've paused the video, you've found the derivative, and if not, you certainly should do so, let's come back together and go through a few steps. Now, if I want to find this derivative f prime x, I could directly apply the quotient rule. There would be absolutely nothing wrong with that. But I just want to point out that we can maybe get there a bit more efficiently in terms of just algebraically simplifying this. And I'll write down a few extra steps just to make sure we're all on the same page. So in terms of simplifying this, we can write this as 1 over x squared plus the square root of x over x squared. That is, in terms of powers of x, we have x to the minus 2 plus x to the 1/2 minus 2, using properties of exponents. And I guess I'll put it way over here to the side. I'll just note x to the a over x to the b is x to the a minus b. So f of x is really just x to the minus 2 plus x to the minus 3/2. And now we have two terms that we can hopefully easily differentiate using the power rule. So for the first term, we would get the derivative minus 2x to the minus 3. And for the second term, the minus 3/2, our in value comes down. And just to make sure we're all on the same page, note that new exponent value is going to be minus 3/2 minus 1. That would be minus 5/2. And if we were to rewrite these without the negative exponents, this would be minus 2 over x cubed minus 3/2 times 1 over x to the 5/2. And all of this work to find the derivative was purely so we could determine this value, f prime of 1, the slope of our tangent line. So f prime of 1 is minus 2 over 1 cubed minus 3/2 times 1 over 1 to the 5/2. And 1 raised to any power is simply 1. So this is going to be minus 2 minus 3/2, which is the number minus 7/2. And minus 7/2 is the slope of our tangent line. And putting this together, we have y as minus 7/2 x minus 1 plus f of 1, which is 2. You could simplify this a bit further, but I actually prefer this form. We can very easily read off the slope along with the point 1, 2, which the tangent line passes through. And this completes the material for the current video, but let me just give you a few reminders. Make sure you're working through suggested problems. If you have questions, reach out to me. And in our next and last video dealing with differentiation formulas, we will go over a few examples from a class worksheet. So yes, this is a time for you to go to Canvas, find that class worksheet associated with differentiation formulas, and spend, 20 to 30 minutes working through those examples. We'll go over a few of them in the next video, but you can also find full typeset solutions on Canvas as well. So stay tuned and take care.